Now I want to look at a corollary, just quickly, of what we just proved. So suppose F is analytic on D, and D is just any open set. Then does that imply F has an antiderivative? No, that's not what we just proved. We proved that if D is a star domain, F has an antiderivative. However, I'm going to claim that F has local antiderivatives, meaning at every point, let's say Z in the domain, there's a neighborhood of Z on which F does have an antiderivative. So since D is an open set, there is some disk, so there's some radius r greater than 0, such that the disk of radius r centered at Z is contained in D, in the domain of the function. A disk is a star domain. In fact, disks are convex, so you could use any point in them as a star center, and that would work. So a disk is definitely a star domain. Let me call this disk U. Let me just call it U. So if I restrict F to just U, then it's an analytic function on a star domain, and so by the Cauchy integral theorem for star domains that we just proved, this has an antiderivative. So a good way to summarize that is to say analytic functions have local antiderivatives. This creates kind of an interesting picture. If you have a domain D and F analytic on this domain, so D just an open path-connected set, and F analytic on it, we don't know that F has an antiderivative, but we know that for any point in D that I fix, there's a neighborhood on which F has an antiderivative. So for this point, there's a neighborhood on which F has an antiderivative. For this point, there's a neighborhood on which F has an antiderivative. For every point, there exists a capital F, possibly different capital Fs, all whose derivatives agree with little f. So I've got this one global little f defined on D, and at every point in D, there's some capital F whose derivative is agreeing with little f. And one way to think about the problem of trying to construct a global antiderivative that works everywhere is that it's kind of a gluing problem. Can you pick antiderivatives, local antiderivatives, at all these different points in such a way that they glue together to make one coherent global antiderivative? So we have seen that you cannot always. For example, we have seen that the function f of z equals 1 over z on the entire complex plane definitely does not have a global antiderivative. So, sorry, on the complex plane with the origin deleted, this definitely does not have a global antiderivative. We know that because we've seen how a contour integral along a certain loop can possibly not vanish. So this definitely does not have a global antiderivative, but it has local antiderivatives at every point. And so something, actually something possibly about the domain or about this function is causing it to be impossible to glue together all those local antiderivatives to create one big antiderivative for this function. And you've seen that you can sort of get an antiderivative for this, maybe on the slit plane. So if you delete a bunch of points, then you've got an antiderivative on quite a large set. It just doesn't glue together properly on the set of points that you deleted.